Okay, welcome back Physics 30s to our next lesson in Chapter 6. This is 6.6, and today we're going to be talking about the de Broglie wavelength. So over this course, we have shifted our thinking about light. We first thought it was just a wave, but now we've seen lots of evidence to show that it sometimes has wave properties, but sometimes has particle properties. And in physics, if a theory applies to one thing, it often applies to another. For example, if you run a current through a wire, it makes a magnetic field. If you move a magnetic field, it makes current run through a wire. So now as our idea of the atom continues to progress and we have this understanding of the Bohr model where we have specific energy levels of the electrons, de Broglie thinks, well, if light, which we thought was a wave, could act like a particle, could electrons, which we think are particles, act like a wave? If this is true and particles can act like waves, they should have a wavelength. So let's use some of our equations to try and calculate the wavelength of an electron. So when looking at photons, we calculated their energy with the momentum is equal to Planck's constant over wavelength. So if we rearrange this for wavelength, we have wavelength is equal to Planck's constant over the momentum. Now that we're talking about an electron, we can put in the equation for momentum for a particle with mass. So we're going to put in P is equal to mv. And we get this equation for calculating the wavelength of a particle with mass. So let's try a calculation and see what is the wavelength of an electron with 2 electron volts of energy. So first, we're going to start with that the energy that an electron would have would be kinetic energy. So EK is equal to half mv squared. To solve for the wavelength up here, I need to determine the velocity first. So we'll rearrange this for velocity and have 2ek over m square root. When I plug in my values, we have to turn the electron volts into joules. So that's this first part here. 2 times 1.6 times 10 to the negative 19 gives us the energy in joules. Times 2 divided by the mass of an electron, square root. We get the number of 3.8 times 10 to the 5 meters per second. Now with the velocity, let's combine that with our equation from above, plug in. Here we have Planck's constant based off of joules. Here we have the mass of the electron and now the velocity of the electron, and we get its wavelength to be 8.68 times 10 to the negative 10 meters. Okay, so if an electron can act like a wave, we have the ability to calculate the wavelength, but where does this apply? Well, although the Bohr model was explaining emission and absorption spectra pretty well based off those energy levels, it doesn't explain how the electron can just exist at those energy levels. If the electron was stationary, it should just fall towards the positive nucleus. And if it was in orbit, it should be emitting EMR because this is an accelerating charge. Well, from some formulas that we don't actually use in this course, we know the electron is not stationary because it has kinetic energy. The energy of the electron we've been talking about is actually its mechanical energy over here. And this is the sum of EK plus EP. And again, using some complex equations that we don't have to go into, it turns out that the potential energy is double the kinetic energy, and we've been treating that EP as negative when talking about those energy shells. So what this means is it actually works out pretty nice for us for determining velocity. So I'll use a simple example here to show that if EK was 4, that would mean that EP would be double that and a negative. So EP would be 8. So then if we take 4 minus 8, we would get a number of negative 4. So when we say the energy, this is what we were talking about with the energy shells in the previous lesson, is negative 4, that actually is representing the same number as the kinetic energy. So when we were looking at negative 13.6 being the ground state for hydrogen, this was an EK, or kinetic energy, of 13.6 electron volts, a potential energy of negative 27.2, and we just wrote this as negative 13.6 as the total energy. Now when we're trying to find the speed of the electron or the velocity, we can use this value for EK. So we know the electron is orbiting the nucleus, but again, it should be giving off EMR and then losing energy. To see why this isn't happening, let's look at the wavelength of that orbiting electron. So here's the diagram that we had from the last lesson with hydrogen's electron in the ground state of n is equal to 1. We also see that its energy is negative 13.6 electron volts, which we now know can represent the kinetic energy. So to find the wavelength of this electron could be a question you're asked in the course. So how we would calculate that is the same process, just using this energy as our last example. So I start with EK is half mv squared, and I would rearrange for getting velocity. Now I'm going to plug in this 13.6 electron volts. We're not worried about any jumps here. It's the energy that it has at this level. So I plug in my 13.6 electron volts. I can convert to joules, times by 2 and divide by the mass of the electron. And I get 2.1857 times 10 to the 6 meters per second. Now with the velocity, I have my formula for the wavelength of a particle with mass. So the momentum here is mv. I'm going to plug into that equation with Planck's constant in joules, the mass of the electron, and the velocity I had from before. And I get an answer of 3.3297 times 10 to the negative 10. Okay, so what's significant about that wavelength? This number is the circumference of the hydrogen atom. Okay, that seems like a pretty big connection. That's saying that the electron going around that n equals 1 value, its wavelength is the same length of its orbit. Now it's hard to imagine with just one wavelength, but this would mean that it completes a lap and then starts where its wave began initially. So imagine going up and down and up and down and reaching that same point that it started, and that would be the same beginning that it had at the start of the wave. It's hard to show with n equals 1, but let's show it with some different values. So again, it's hard to show for the first ring, but for the second one, this would have multiple wavelengths. So it looked kind of like this. So imagine that this is a wave that has been just looped back on itself. So the electron is going to go up, come back down, go up, back down, and around. And it's going to be moving like this. This is the wavelength of the electron put into an orbital, and it matches the circumference of that orbital. I think it's even easier to visualize with this energy state further away from the nucleus, as we can see the peaks and troughs. And the electron is going to be traveling through those peaks and troughs in that wavelength. And the wavelength matches up so that it creates a standing wave in this circumference. So this is de Broglie's explanation of the Bohr model, and it kind of makes sense in that this is why it's allowed to be at one energy level or the next, because it needs to make a standing wave. So if you increase the radius and it doesn't match a standing wave, the electron can't exist there. It only exists in levels where it can be a standing wave. Now this is seeming to make some sense, however it's a pretty big claim for de Broglie to say that an electron acts like a wave. But remember, we had this experiment by passing things through a double slit to see if they acted like a particle or a wave. So let's do that with the electron. So I have here these two slits, and I'm going to fire electrons at them. And we would expect that if it acts like a particle, we'll just get two bright fringes over here. And we start firing the electrons one at a time, and we get one here, and here, and here, and here. And these, well, maybe this is kind of one of those bright bands, and this is going to be the next one. But when we fire an absolute ton of them, we get this pattern. That looks like a pretty convincing diffraction pattern to me. This confirmed the idea that a particle can act as a wave, and it changed a lot of our thinking about particle-wave duality. This is still a really hard concept to wrap your head around, and it doesn't really seem very intuitive. To make it even a little bit more weird, this actually isn't a wave of the electron moving up and down. We can more think of it as a probability wave. The electron is so small, and based off its energy and momentum, we can't really predict exactly where it is, and this is more of a wave of probability where we think it's most likely to be. Again, that's hard to wrap your head around, and we'll talk about that a little bit more in class, but we use the analogy of the electron moving through the wave in that diagram I showed before. So hopefully that's made some sense for you. Mostly what you're going to get asked in class is to calculate the wavelength of an electron at these different shells. So I hope that has helped you to do those calculations. Ask me any questions that you have in our class time, and I will see you in the next video.